Hi, I'm Dr. Jason Brinkley, and this is Acids and Bases. By the end of this video, we will be able to classify compounds with acid-base properties as acids, bases, or amphiprotic. We'll also write equations illustrating the role of water in acid-base reactions, identify conjugate acid-base pairs, describe the relationship between acid and base strength and dissociation, and use the ion product constant for water to solve for hydronium and hydroxide ion concentrations. So what is an acid? Well, it depends upon what theory we're using as to what an acid is or what a base is. The first theory we're going to talk about is the Arrhenius theory. Now, Arrhenius worked with solutions and he did something unthinkable. He tasted them, and he found out that acids were sour. And he found out that all acids are going to be substances that produce H plus ions in water. Okay? And a base is something that's going to be bitter and produces hydroxide ions in water. And H plus reacts with OH minus to form HOH or H2O. So an acid-base reaction is, in the Arrhenius definition, hydrogen plus hydroxide, hydrogen ion plus hydroxide ion makes water. So you can see here HCl donates a proton or donates an H plus ion in water, and we have the counter ion chloride. Similarly, sodium hydroxide donates a hydroxide ion and the sodium counter ion. You can tell acids because they're going to start with H's for the most part, unless they are organic acids. We'll talk about those in just a few minutes. And then bases are always going to contain hydroxides in the Arrhenius definition. But there is a problem with the Arrhenius definition. H plus is a bare proton. Now, a bare proton is not going to be flying around in solution. It is going to attach to something because it needs to have electron density around it. That's what we get with Bronsted-Lowry acid-base theory. Now, an acid is a proton donor. Which is the same as basically an Arrhenius acid, which gives off an H plus ion. But a base is a proton acceptor. Now, what this really does is it expands what a base can be. Water can act as a base. In fact, water can actually act as a base or an acid. We'll talk about that again in a few minutes as well. But HCl plus water forms the hydronium ion, H3O plus Cl minus. So whenever we see H plus in solution, what we really mean is it's the hydronium ion, the H3O plus. Okay? Now, as I said, water can act both as an acid and a base. In the previous example, water acted as a base. In this example, where we have ammonia reacting with water to form the ammonium ion and the hydroxide ion, water is acting as an acid to donate one of its protons to the NH3 to form NH4 plus and the hydroxide ion. Okay? This is the term amphiprotic, and we'll talk about that at length in just a few minutes. As I stated, organic acids are a little different. Organic acids are what are known as carboxylic acids. They have the functional group COOH, which is carbon double bonded to an oxygen with an O and an H. This is the acidic hydrogen at the end of that OH group. Now, organic bases are often going to contain nitrogen. So something like methylamine. The nitrogen is going to be the basic portion of this molecule. Now, under the Bronsted-Lowry acid-base theory, we have what are known as conjugates. Okay? Now, the acid that donates a proton in a chemical reaction becomes a Bronsted-Lowry conjugate base. Okay? I'm going to say that again. The acid that donates a proton in a chemical reaction becomes a Bronsted-Lowry conjugate base. In other words, the counterion is a base. And the base that accepts the proton from the acid becomes a Bronsted-Lowry conjugate acid. Okay? So, for example, take a simple acid HX, something like HCl or HBr or HI, and a base Y. The acid donates a proton to the base to form HY plus, and we're left with X minus, the counterion. The acid and the conjugate base are related. They're what we call a conjugate acid-base pair. And the base and the protonated conjugate acid are also a conjugate acid-base pair. Okay? So here we have CH3, CH2, COOH plus H2O goes to H3O plus CH3, CH2, COO minus. This is our Bronsted-Lowry acid. This is our Bronsted-Lowry base. The base, which accepts the proton, becomes the conjugate acid. And whatever's left over from the Bronsted-Lowry acid becomes the conjugate base. So the Bronsted-Lowry acid and conjugate base are related, and the Bronsted-Lowry base and conjugate acid are related. Similarly, with ammonia and water, here is our Bronsted-Lowry base. Here's our Bronsted-Lowry acid. This is our conjugate acid and our conjugate base. So the Bronsted-Lowry acid becomes the conjugate base. The Bronsted-Lowry base becomes the conjugate acid. So let's classify each of the following compounds as either a Bronsted-Lowry acid or base. So we've got PO4 3-. There is no H+, so we can't donate a proton. So this must be a Bronsted-Lowry base. CH3 NH3+. This is the conjugate acid of CH3 NH2. So this must be a Bronsted-Lowry acid. Because this is a Bronsted-Lowry base, this must be a Bronsted-Lowry acid. HI, we're starting with H, so this must be an acid. And H3PO4, this must also be an acid, a Bronsted-Lowry acid. Anything that starts with an H is going to be an acid in both the Arrhenius definition and the Bronsted-Lowry definition. Now, water, as I said, can act as an acid or a base. It is amphiprotic. We can see, again, HCl plus H2O goes to H3O plus the Cl minus ion. That's water acting as a base. And then we've got the NH3 plus H2O forming NH4 plus and OH minus. This is water acting as the Bronsted-Lowry acid. There are many substances that are amphiprotic that act as both an acid or a base. One that is very important to human life is the bicarbonate ion, HCO3-. We can either gain an H to form H2CO3, or it can lose an H to form CO3 2-. So that is an amphiprotic substance as well. Let's write an equation for the reversible reactions of each of the following with water. H3PO4. So let's start off with A. H3PO4 plus H2O. Now, H3PO4 is an acid, so it's going to donate a proton, and they said this is a reversible reaction, so we're going to use double arrows. It is going to donate a proton to the H2O to form H3O plus, and whatever's left over becomes our conjugate base, which would be H2PO4 with a minus charge. It's a minus charge because we lost an H plus. Okay? Similarly, let's do B, which is methylamine, CH3NH2 plus H2O goes to CH3NH3 plus OH minus. Now, the strength of acids and bases are very important in that we need to know whether a base or an acid is strong or weak. A strong acid and base is something that completely dissociates in water. There are 7 strong acids: HCl, HBr, HI, HNO3, HClO4, HClO3, and H2SO4. It's important to know what are your strong acids because then you can know what are your weak acids. If it's not one of the strong acids, it must be weak. Our strong bases are group 1A hydroxides, which include sodium hydroxide and potassium hydroxide and the others, as well as the heavy group 2s, calcium hydroxide, strontium hydroxide, and barium hydroxide. And again, with weak acids and bases, these are all the other acids and bases that you could run into. So it's important to know, memorize the strong acids and bases so that you know what is strong and what is weak. Now, strong acids, as I say, completely dissociate into ions in solution. So here we have a strong acid before ionization. It's all HCl. At equilibrium, it is equal H3O plus and Cl minus. You can see the H3O plus and the Cl minuses at equilibrium. A weak acid before ionization is CH3COOH, something like acetic acid. And you can see the molecules of acetic acid are still present at equilibrium. Only a small amount of H3O plus and CH3COO minus are present at equilibrium. That is because they do not dissociate completely in water. That is the definition of a weak acid or weak base. Now, the stronger the acid or the stronger the base, the weaker the conjugate. So, for example, we've got our strong acids up here, HCl, H2SO4, HNO3, and H3O plus. These all have very weak conjugate bases. So HSO4, which is a weak acid, has a stronger conjugate base than H2SO4. And as you go down, the weaker the acid, the stronger the base, until you get something like water, which is a very weak acid. Its conjugate base is hydroxide ion, which is very, very strong. Okay? So the stronger the acid, the weaker the conjugate base. The stronger the base, the weaker the conjugate acid. So let's take a look at each of these pairs and identify which is a stronger acid. Is H2O or NH4 plus a stronger acid? Well, in this case, H2O would dissociate into H plus OH minus, which we know happens, but to a very small extent. NH4 plus is the conjugate acid of a weak base. Therefore, it is a stronger acid. Okay? H2SO4 or H2SO3. H2SO4 is a strong acid. H2SO3 is not one of our strong acids, therefore it must be a weak acid. So the stronger acid is H2SO4. Then we have it's asking us to write the conjugate acid of each base and identify the stronger base. I forgot to write the conjugates. But the conjugate acid of CO3 2 minus would be HCO3 minus, and for PO3 or PO4 3 minus it would be HPO4 2 minus. It's a 2 minus because we've added an H plus. The stronger base is going to be the weaker acid. So the weaker acid is phosphoric acid. So PO4 3 minus is going to be the weaker or the stronger conjugate, or the stronger base. HCO3 or HPO4 2 minus is going to be H2CO3 and H2PO4 with a 1 minus. In this case, this is still a stronger base because this can't accept another proton. So this is a stronger base. Now water, we talked about, can actually react with itself. It's what is called self-ionizing. So water reacts with itself. H2O plus H2O forms H3O plus and OH minus. Now it does so in such a fashion that we get a equilibrium constant Kw. This is equal to H3O plus times OH minus. And this is a constant. The constant is 1 times 10 to the minus 14th, which means that at equilibrium, the concentration of H3O plus and the concentration of OH minus must be the same, and they must be 1 times 10 to the minus 7th molar. Now, since this is the ion product constant, increasing the concentration of one results in a decreased concentration of the other. So if you increase the H3O plus, OH minus must go down, and vice versa. So let's do an example of this. The hydroxide ion concentration in a sample of urine was determined to be 1.0 times 10 to the minus 8th at 25 degrees C. Calculate the hydronium ion concentration of this aqueous solution. So we know that Kw is equal to the concentration of H3O plus times the concentration of OH minus, which is equal to 1.0 times 10 to the minus 14th. If the hydroxide ion concentration is known, and that is the 1.0 times 10 to the minus 8th, then we can calculate out the H3O plus, which is our unknown. So this becomes H3O plus is equal to 1.0 times 10 to the minus 14th over OH minus, which is equal to 1.0 times 10 to the minus 14th over 1.0 times 10 to the minus 8th. And that tells us, when we do this on our calculator, our hydronium ion concentration, 1 EE negative 14 divided by 1 EE negative 8, and we get 1.0 times 10 to the minus 6th molar. As you can see, as one decreases, the other one must increase in concentration in order to keep the ion product constant. I hope you've enjoyed this video and this introduction to acid bases, and I look forward to seeing you in the next.